Where and how you park a grow bus or situate a conventional greenhouse determines how warm and sunny it is at different times and ultimately determines how well plants can thrive in such a structure. This video will explain what to consider when placing a passive solar structure and will involve a lot of thinking about sunlight, which is kind of nice this time of year. This bus is parked in completely the wrong orientation with respect to north, south, east, and west. Right now, this bus is parked facing north. And if it's facing north, the sun will rise just kind of behind it, then kind of pass over the back of the bus, and then set on the other side, but still only really hitting the back of the bus. When you're situating a greenhouse in the northern hemisphere, you want the side that's facing the south to be at least twice as long as the side that might be facing east or west, as those directions only really receive direct sunlight at the beginning or the end of the day. The shadow casting feature of the free software Sketchup can demonstrate this. Here in Sketchup, I've geolocated 2 copies of the Growbus model in a potential parking space on the farm. One bus is oriented as recommended for a greenhouse with its sides facing south and north, whereas the other bus is oriented with its side facing east and west. This orientation is inefficient. We'll instead look at how this recommended orientation presents way more surface area for sunlight capture. Here on April 25th, you see the sun rise in the east, pass overhead just to the south side of the bus, and then set in the west. I chose late April because that's the beginning of the growing season we're considering, but this is noon from January through to midsummer here, and then back to December. Throughout the year, the shadow at noon is on the north side of the bus. Switching back to April 25th, we can compare the sun exposure on the north side and south side of such a situated bus and see how much more exposure is on the south side as compared to the north side here in the northern hemisphere. This bus is parked at 36 degrees north latitude. Online, you can generate one of these solar elevation charts, which indicates where the sun will be in the sky at your latitude on any given day of the year. The blue bell-shaped lines trace the path of the sun as it goes from east to west along the x-axis and vertical angles over the horizon along the y-axis. The red curves indicate the time of day over the course of the months, which are concentric parabolas or bell curves, with the winter months lowest on this chart and the summer months at the top. Here inside the bus is the best place to describe how solar elevation, or the angle that the sun makes at the horizon, relates to what objects can be outside the bus shading it, or how much these sidewalls shading the interior here. Rather than modeling the entire grow bus super accurately in SketchUp, we can instead take some length and height measurements and use a touch of trigonometry to figure out what was going on with these shadows. Trigonometry. Okay, SOHCAHTOA. Tangent of the solar elevation angle theta is equal to opposite the height of that sidewall over adjacent, the length across the floor. This calculation results in a solar elevation of about 20 degrees. For completeness, we can repeat this calculation with the height to the top of the windows. This resulted in a solar elevation theta taller of 32 degrees. Having calculated the solar elevations to the bottom and the tops of the windows, we now have a range of solar elevations for which direct sunlight is streaming through those side windows and incident on the base of that back wall. So let's map those solar elevations on the solar elevation chart, find out when during the year the sun will be at those solar elevations. Looks like during these winter months, the sun only ever passes through the windows rather than the roofing. Whereas during warmer, sunnier months, each day the sun passes through those low elevations and onto the higher elevations at which sunlight has to pass through the roofing for direct sunlight to illuminate the north side of the bus floor. Total internal reflection is an optical phenomenon which limits the amount of light that's transmitted through the glass at solar elevations greater than 45 degrees. Because for these vertical glass pane windows, a solar elevation of 0 degrees would be exactly perpendicular to the surface, so it would have the highest transmittance. This diagram is a helpful visualization. So this breakdown of the solar elevation chart governs the contribution of the side windows to sunlight that directly interacts with the floor of the grow bus. Installing a clear or glazing material on the roof of the bus also faces these same concerns about total internal reflection. It's just more complicated because the roof is curved. so I made it flat. Yes, now that's nicer to think about. So any solar elevations less than 45 degrees wouldn't get through this roof. But a flat roof would get covered in debris and might collapse, so we'll add another level of complexity. Its roof isn't that sloped. It's pretty close to flat. There's some curvature at the sides. I was convinced. So I took some Euclidean measurements on that mostly flat curved roof, connected them with hypotenusa, apply the Pythagorean Theorem, then apply the tangent function, just as before, to figure out that that center section was sloped about 10 degrees and the outer section was sloped about 53 degrees. Now let's see how these approximate slopes shift the ranges of solar elevations that are excluded by total internal reflection. For a flat surface, only solar elevations that were greater than 45 degrees would allow direct sunlight to be transmitted. However, for the sections of the roof that are slanted about 10 degrees towards the south, where the sunlight is generally coming from, an extra 10 degrees lower solar elevation still allows light into the bus. However, on the north side, with a slight tilt, direct sunlight will not be transmitted until 45 degrees plus 10 degrees, so a solar elevation of 55 degrees is achieved. These solar elevation minima, as governed by total internal reflection, are displayed here on this solar elevation chart. About 90% of the surface area of the bus's roof is included in this slightly slanted approximation. So the transmittance of the vast majority of light that is incident on the roof of the bus is governed by the limits designated on this solar elevation chart. For completeness, we'll move on to more steeply slanted sections of the roof. If you think of taking those two 45-degree off perpendicular bounds and shifting them 53 degrees towards the south or 53 degrees towards the north, this creates no bounds on the solar elevations on the south-facing side, but completely eliminates the contributions to direct sunlight exposure on the steeply sloped north-facing section of the roof. Solar panels deal with the same issues of having the incident light as close to 90 degrees on the panels as possible. Fortunately, with the bus, there's also these side windows that take a completely different angle and therefore can utilize that early morning or throughout the winter light more than a traditional solar panel. It's like having two solar panels aligned. So you'll see there's solar panels that kind of like follow the sun, or at least over the year kind of angle. During the summer months, you want the slope to be your latitude minus 10 to 15 degrees, and then in the winter, you want it to be your latitude to like 36 plus 10 to 15 degrees. So it creates more of a south-facing angle and utilizes those days like this one here on the solstice, where the sun is keeping a pretty shallow arc over the horizon. Whereas in the summer, it's not quite such a limiting factor because the sun is going to have these big sweeping arcs over the horizon, even if you're at pretty high latitudes. We're a little bit far north for it to be perfectly angled according to that heuristic. It's still worth the investment of installing a glazing material on the roof to make sure that the light gets in to the interior of the bus. So that's the plan.